So let's go ahead and get started. So this is our third lecture on linear programming. A week ago, I tried to convince you that linear programs model lots of different problems that we care about. So we should care about understanding them. We should care about algorithms for them. And then on Thursday, we started our discussion of linear programming duality, which we're also going to be discussing all day today. And really, LP-duality, I think in hindsight, after you finish the course, you'll recognize it as really sort of the heart and soul of CS261, really kind of the concept that binds an enormous, overwhelming majority of the concepts that we're going to discuss. So, I know that was 5 days ago, and it was a pretty conceptually rich lecture on Thursday, so let me help you page back in sort of where we left off. So, if you have a linear program of the following form, so a maximization linear program subject to inequality constraints with non-negative random variables, we talked about the idea of generating upper bounds on the best possible objective function value of this linear program by taking suitable linear combinations of the constraints. And then we noticed that looking for the tightest upper bound of this form is itself a linear program. And that linear program is called the dual. And in general, what happens when you pass to the dual, min goes to max, max goes to min, variables turn into constraints, constraints turn into variables, the objective function on the right-hand side gets swapped, and the constraint matrix gets transposed. Okay, that's sort of what's happening here. So you can see some of it more clearly in the vector matrix notation, which I've listed in pink. So for example, you can see here that the constraint matrix gets transposed when you pass to the dual. So this is just one particular form of a linear program, and as we've discussed, there's many forms. You could have equality constraints instead of inequality constraints. You could have general real valued variables instead of non-negative variables. You could have a min instead of a max. And last time we talked about how to take the dual of any linear program. And we'll actually use that general recipe today when we return to bipartite matching. Okay? All right, so once we understand the meaning of the dual linear program, once you understand that every feasible solution to the dual is by construction, gives you an upper bound on the primal objective function value, at least for the maximization case, then weak duality is self-evident, right? So basically, every dual solution has an objective function value which upper bounds the objective function value of every primal solution, feasible primal solution. That holds in particular for the optimal solutions to the primal and the dual, from which we can conclude that the optimal solution of the primal is at most the optimal solution of the dual, okay? If the primal is a minimization linear program rather than maximization, then this inequality goes the other direction, okay? So just to remind you, and also for reference, here's the proof of weak duality. And so again, what this is showing, it's saying take anything, any x feasible for the primal, take any y feasible for the dual. Let's show that the objective function value of x, which is this, is bounded above by the objective function value of the dual solution y, which is this. Okay? And again, it holds in particular for the optimal x and the optimal y. And so how do you do this? Well, you just invoke, for this inequality, you invoke that y is feasible for the dual. So these linear combinations A transpose y of the constraints dominate the objective, dominates C. We're also using here that x is non-negative. So by making this bigger, we only make the overall quantity bigger because all of these are non-negative. This is just association. And over here we're using similarly that x is feasible and that y is non-negative. Okay? So we did that derivation last time. This is just a succinct reminder. And again, that picture you might want to have in mind is the same one I drew when we talked about the value of a flow being at most the value of a cut. So again, this is for the case of a maximization primal, otherwise it would be reversed. So, we can plot on a line sort of possible objective function values. The x's are the objective function values that can be attained by feasible solutions to the primal. The o's are the objective function values in the dual that can be obtained by feasible solutions for the dual. Weak duality says all the o's are only to the right of all the x's. Okay? And one thing that gives us immediately is a sufficient condition for optimality. It's not clear if it's necessary yet, but it will be necessary in the end. So a sufficient condition for optimality would be that you have a superimposed x and an o. That is, that you can find feasible solutions with equal objective function value. Okay? This proves that both x and y are optimal for their respective linear programs. Why? Well, no x can be strictly to the right of any o. So if you have an x exactly with an O, then that's got to be as rightmost as any x could be. It's got to be an optimal primal solution. Similarly, you know O can be the left of an x, so if you can actually superimpose with an x, you got to be optimal. Okay. And then the last thing that I left you with on Thursday was complementary slackness conditions. So let me remind you about those and also explain why they're true, or why they're a sufficient condition for optimality. So complementary slackness, this is sort of a corollary of that corollary. So the complementary slackness conditions. So again, suppose you have x, y feasible for the primal and dual respectively. And suppose it's the case that over in the primal, the only time you give a non-zero value to a decision variable is when the corresponding constraint in the dual is tight, meaning holds with equality. So remember, every variable in the primal corresponds to a dual, constraint in the dual. Every constraint in the primal corresponds to a variable in the dual. So you can talk about saying a primal variable xj, it is only non-zero when the corresponding constraint, so the jth constraint of the dual is tight, i.e. holds with equality. Okay? So that's one of the two conditions. Primal variables are only non-zero when the corresponding dual constraints are tight. And then we also have a second condition which goes the opposite direction, which says that a dual variable should only be non-zero when the corresponding constraint of the primal is tight. Okay? So again, the ith decision variable in the dual is in correspondence with the ith constraint in the primal. So we can talk about the corresponding constraint in the primal being tight. Okay? All right, so that's the hypothesis. Suppose you have feasible solutions that satisfy 1 and 2. Then we get the same conclusion as before. Then x, y both optimal. Okay? So what I want to do next is prove this. Before that, so this brings us back up to date with where I left off on Thursday. So any questions about the recap or about the big picture? All right. So the proof of this is actually staring at us on the top board. So suppose x and y are feasible, and suppose 1 and 2 hold. Let's stare at that circled derivation up there. That proves that the objective function value of the primal is always at most that of the dual. I claim that the point of conditions 1 and 2, what it buys us, is it allows us to conclude that both of the inequalities in the circled derivation are actually equalities. So in the weak duality proof, 1 plus 2 imply that both inequalities are actually equalities. Okay? So this might be a little bit easier to see if I switch back from matrix vector notation back to the sums. So for example, focus on this first inequality here, C transpose X is at most this other thing. So Y transpose AX, Y transpose A transpose X. And consider a single term, right? So C transpose X is the sum over J of Cj Xj, just consider some fixed J. So if 1 holds, then I claim that for all J, Cj Xj just equals Xj times sum over I Aij Yi. Okay? So again, this is for a fixed J. That's just one ingredient of each of these numbers, right? So these are all scalars, right? This is a sum of a bunch of scalars summed over j. Same thing here. I'm saying coordinate by coordinate, the terms match. Okay? And if you look at it this way, it should now sort of be obvious. Okay? Case 1, xj is 0. Both sides are 0. No problem. Case 2, xj is not 0. Well, then just the condition tells us that the corresponding dual constraint holds with equality, i.e., this number actually equals this number. Okay? So either xj is 0 and you're done, or the equality or the thing is tight and you're also done. All right? So it's called complementary slackness because it's just asserting that you don't have slacks simultaneously in the primal and in the dual. Okay? If you think about a non-zero value corresponding to having slack in the primal, and you think about being strict inequality, having slack in the dual, you never see both of those at once. That's the condition. If the condition holds, then, because the circle derivation holds with equality, that proves that the objective function value of the primal and the objective function value of the dual are the same. And by our previous corollary, that says they both have to be optimal, just by the x's and o's argument. Okay? So that's complementary slackness, and that's why it's true. Okay? So next I'm going to do a couple different things which are less abstract, more concrete, should help you understand this better. But any questions just about sort of the abstract versions of these concepts before I continue? Okay. So one thing which I offer to you sort of purely as a metaphor, not as anything formal or precise, but that seems to be helpful for students sometimes, is a way you can kind of physically think about or interpret complementary slackness conditions. Okay? So suppose you have a linear program and you've got some direction, some objective function, and then you're going to have some optimal solution x star. Okay, the point furthest in the feasible region in that particular direction. So if you want, you can think about the objective function as effectively exerting force. Force in the direction c. Okay? And you can think of these as sort of physical walls, right? So the sides of the feasible region. Okay? So basically, in optimizing this linear program, as we sort of discussed before, you're pushing in a particular direction until you can't go any further. And in general, except for some edge cases, you're going to wind up at a vertex, at a corner. Now, at this point, once you get to x star, there's no longer any movement. Okay? X star is just holding there, despite the fact that the objective function is still exerting force in the direction c. So if there's no motion, then somehow the sum of the forces acting on this point should add up to 0. So what else is exerting force on the point other than the objective function? Well, the sides, or if you like, the constraints, can also exert force backward, okay, in the opposite direction. The direction of that force exerted by one of these walls is going to be given by the normal to that hyperplane, okay? You can then interpret these yi's. So previously we were interpreting the dual variables as multipliers of the primal constraints. For this physical intuition, you can interpret the yi's as the magnitude of the force being exerted in this particular direction. Okay, being exerted in the direction of the normal vector of the ith constraint. Okay, so remember, dual variables correspond to constraints. So we have one dual variable for each of these sides. So if this is motionless, the sum of the forces should be 0. Now what does complementary slackness say? Okay. So the version I'm looking for is this version. So let's look at condition 2. So yi is strictly positive only if that corresponding constraint in the primal is tight. That just says that any of the sides of the feasible region which don't actually touch where the point gets stuck, they're not allowed to exert any force on this point. Okay? Because they don't touch it. On the other hand, anything which is tight, so knows these correspond to two tight constraints, these two sides of the feasible region. So anything that is tight can exert force, and then you're looking for a sum of those forces which equals sort of the opposite of the objective function value. Okay? So if you like, this is one way to think about complementary slackness. So basically the only things that can exert force on a solution are the constraints that are binding. Okay? The constraints that are touched by the optimal solution. Okay. So why am I telling you about complementary slackness? What are they good for? Well, if you think about it, if we take a step back, so we talked about when we were solving max flow and then again when we were solving matching, how these sort of harder problems in P required sort of discipline. They require really a strategy to solve them correctly. So you almost have to sort of be thinking about how you're going to prove an algorithm correct when you're designing the algorithm itself. Complementary slackness provides a very general paradigm, really 3 different paradigms for these kind of discipline strategies for solving problems. So what do I mean? Well, consider 3 conditions which may or may not be satisfied at any given point. So you have some kind of attempted primal solution. You have a y, and you have the complementary slackness conditions. What did we just say? We just said if 1 through 3 are all satisfied, then x and y are both optimal. Okay, so we know that. Now, when you want to solve a problem from scratch, you don't expect to just zip straight to the optimum. So the general paradigm would say, well, of the 3 things which together are sufficient for optimality, pick 2 of them that you're going to keep satisfied at all times in your algorithm. You're going to violate the 3rd one initially and work toward restoring the 3rd condition. Okay? So the paradigm would say, pick 2 to maintain at all times, so as invariance. Work toward the 3rd. Okay? So you could start with a feasible primal and a feasible dual, presumably not optimal, maybe just sort of initializations, and then work toward complementary slackness. You could start with a primal solution that's feasible, an infeasible dual and complementary slackness, and work toward dual feasibility. Or you could start by violating the primal feasibility constraints, maintain a feasible dual and complementary slackness as invariance. Okay? So it turns out an enormous fraction of the polynomial time algorithms, or just the useful algorithms for linear programming and also special cases like we've been talking about, are in fact instantiations of this general paradigm. That's exactly what they do. In fact, maybe one of the most transparent examples of this design paradigm is an algorithm you already know, the Hungarian algorithm. So what I'm going to show you next is that the Hungarian algorithm indeed maintains 2 and 3. Okay, it maintains a dual feasible solution at all times. It maintains complementary slackness at all times. And it works toward primal feasibility. And the reason, now in hindsight, now that we understand linear programming duality, we can say the reason the Hungarian algorithm is correct is because it halts with primal feasibility, dual feasibility, and complementary slackness. Okay? So that's really kind of the sophisticated way to think about the Hungarian algorithm. And we're now in a position to have that kind of understanding. Okay. All right. So, sort of a case study of LP-duality and complementary slackness. A problem we've already seen. Min cost, perfect, bipartite matching. Okay? Example number 2, maybe you don't remember example number 1. So example number 1 on Thursday was max flow. Okay? So what did we do? We showed that you could formulate the maximum flow problem as a linear program. We took the dual of that linear program and we tried to interpret it, and we observed that actually ST cuts of a graph correspond to a special case of dual solutions which are 0, 1. And then we interpreted the fact that the max flow min cut theorem is true. That gave us 2 interesting implications back with flows and cuts. First of all, it verified strong duality for a particular type of linear program, namely flow-cut primal-dual pairs. And secondly, it gave us an interesting example of a linear program that is guaranteed to have optimal 0, 1 solutions. Okay? So even though the linear programming relaxation of ST cuts allows fractional solutions, they never actually help you. Okay? Always is going to be a 0, 1 solution, which is optimal. So that's all recap from example number 1. So now we're going to do example number 2. Okay? And we'll see some of the same themes reoccur. Oh yeah, right. And so, and actually if you think about it, you know, I started with maximum flow because it's almost obvious that maximum flow is immediately a linear program. But I claimed earlier that linear programs generalize everything we've discussed so far. And if you think about matching, all of a sudden that maybe seems kind of weird, right? Because when you have flows, flows are allowed to be fractional. Okay? So no big deal that a linear program might have fractions. Matchings are not allowed to be fractional, right? They really have to pick an edge or not pick an edge. So it seems doesn't seem to type check really to talk about a linear program solving the matching problem, because what's up with the fractions? But again, you know, we have this sort of inspiration from our work on ST cuts showing that sometimes you have a linear program and just there's always going to be an optimal 0-1 solution. So that's also going to be what happens here with bipartite matching. Okay. So what's the relevant linear program for min-cost perfect bipartite matching? Well, so of course we want to minimize the cost of our solution. In our minds, we're thinking of XC as being either 0 or 1. 1 if it's in the chosen matching, 0 if it's not in the chosen matching. Okay, now, of course, this can be a linear program. We don't know a priori we're going to get 0s and 1s, but that's the semantics that we have in mind. So what are the constraints? How many constraints do we have? One constraint per what? So we have one decision variable per edge, right? The decision variables are the XEs. So what are the constraints? Say it again?
We need one edge.
Exactly. So we're going to have a constraint for every vertex, which enforces it being a perfect matching. Mm-hmm. Okay. So I'm using the same notation as a couple weeks ago. It's a bipartite graph, so two sides, capital V and capital W, with the same cardinality. Delta V denotes the edges incident to V. So we look at how many edges get chosen incident to V, and this should be equal to exactly 1. Okay. At most 1, because it needs to be a matching. At least 1, because it's supposed to be perfect. Okay. And of course, non-negativity. Okay. You might think about also including constraints that say XE is at most 1, but those constraints are already implied by the constraints that we have so far. Okay. So if the x's are non-negative and they sum to 1 around every vertex, then automatically each x sub b at any feasible solution will be at most 1. And so again, just looking ahead to the dual, it might be easier to write this in matrix vector notation. So this here is the all ones vector, because the right-hand side is all ones. Okay, so any questions? Yep.
So what happens if the solution is a fractional edges? Like how do you?
Good question. Basically, that's kind of like an epic fail for now. Okay, so we're basically hoping that doesn't happen. All right, now so I have to justify. It turns out that's not going to happen, but I have to justify that. That is far from obvious. Yeah, good question. Other questions? So what I hope is clear is that if I give you a perfect matching, you can certainly translate that to a feasible solution to this linear program. Okay, just by setting XE equal to 1 for the edges in the matching and X equals 0 for the others. And the cost of in the objective function will be exactly the same as the cost of the matching, as the way we normally define it. Okay. So any questions before we move on to the dual? Okay. So notice that this dual is not, or sorry, this primal is not in the sort of form, the same form as in the, say, the max flow problem, okay? Or the one that we started with on the board at the beginning of lecture. What are the differences? We don't have a max, we have a min. Okay, so that's different than before. Also, the constraints are equations, not inequalities. Okay? But Thursday, I gave you a general recipe for taking the dual of any linear program, no matter what the form, including this form. Okay? So I'm going to go ahead and take the dual. And you may want to double check the recipe I gave you Thursday out after class to make sure that you understand why I did what I did. Now, when you take the dual, it's nice to try to understand what the dual means. Okay? So it's nice if there's a meaningful interpretation of the dual. And usually, the hardest thing to figure out what's going on is what happens when you transpose the constraint matrix. So remember, the dual has constraint matrix A transpose, where A is the constraint matrix of the primal. So what is A for this particular primal? So the columns are indexed by what, first of all? Columns are indexed by what? It's kind of two possibilities, right? Vertices or edges? Edges. So the columns correspond to the decision variables. The decision variables for this linear program are the edges. And so the constraints then, the rows correspond to the constraints. Those correspond to the vertices. Okay? So inside this matrix, a generic entry will be indexed by a vertex and an edge, A sub V sub E. Okay, the row corresponding to V and the column corresponding to E. So first, let's just remember what capital A is. So in capital A, the rows just correspond to these constraints. So fix a row, that is, fix a vertex V. Where are there zeros and where are there ones? Okay, so notice the constraint. There's some x's with a coefficient of 1, and the rest don't appear. Okay, so the corresponding row of A has zeros and ones in it. It has a 1 corresponding to exactly the decision variables that appear in that constraint. For a given vertex, which variables appear in that constraint? Well, exactly the edges that are incident to that vertex. Okay? So if you fix a row of this constraint matrix and you scan left to right across all the edges, you're going to see a 1 exactly when you're looking at an edge which is actually incident to V. Okay? So this is going to be equal to 1 if E is incident to V and 0 otherwise. Okay? And so how do we figure this out? We figured this out by looking at the constraints of our primal and asking what do those look like as rows. Okay? Now taking the transpose of a matrix is easy. Okay, so what have we done? We've translated the sums into a matrix. Looking toward the dual, we can easily transpose this matrix. But now if we want to write out the constraints of the dual in a meaningful way, we have to understand what these coefficients are. That is, we want to think about a column of this matrix, because that's going to correspond to a constraint in the dual. So suppose I fix an edge, E. Okay, so corresponding to a column of A. And I scan down. I scan through the vertices. When do I see a 1 and when do I see a 0? Well, how about this? How many 1s am I going to see as I scan down? I'm only going to see 2. Okay? For the 2 vertices for which this edge is incident to, i.e. the 2 endpoints of the edge. Okay? So each column of A, that is each row of A transpose, just has 2 1s corresponding to the 2 endpoints of the edge. Okay? All right, so now we're ready to just sort of write this down. Okay? So first, again, let me just do it in matrix vector notation. So what's going to happen? So the min becomes a max when you take the dual. The objective and right-hand side get exchanged. So this is going to be, let's see. So the right-hand side was all 1s, so we now have that. I'm going to use P to denote the decision variables for reasons that will become clear. All right, so the constraints here correspond to vertices. So over here, the dual variables are going to correspond to vertices. I'm going to write them P sub V. Okay, and so then we have non-negativity constraints here. So we're going to have inequality constraints in the dual. So So we have A transpose, as usual, decision variables. This is a maximization problem. So it's going to be an inequality because these are not negative. And this is the direction of the inequality because this is a maximization problem. And the new right-hand side is the old objective function, so that's C. Okay? And then the final twist in that recipe would be here we have equations, not inequalities. So what that means in the dual is that the corresponding dual variable can be positive or negative. It's not restricted to be non-negative. If this was an inequality, we would get non-negative dual variables. With an equation, we get unrestricted dual variables. Okay? So each dual variable is just a real number. So that's what you get if you apply the recipe from Thursday. So again, let's unpack this. All right, so this inner product, this is just the sum of the p-values. Okay? So we're maximizing sum of the p-values, sum of the dual variables, subject to. All right, so let's remember what this is. So a given dual constraint corresponds to a primal variable, so corresponds to an edge. We agreed that in a row of A transpose, you only see two ones, okay, corresponding to the two endpoints of the edge. So we're going to have a constraint. All right, so again, remember, constraints correspond to variables here. So we have one constraint per edge. Call your favorite edge v comma w. Which dual variables are going to show up in this constraint? It's exactly the ones for which there's a 1 in A transpose, so it's exactly the endpoints of this edge. So we have a piece of v. We have a piece of w. Okay, so that's A transpose p in this particular row. And this is at most the coefficient in the primal objective function for this edge. Okay? So that is the dual. All right. So any questions about that? And so I hope in sort of watching me take a dual step by step like this, you can really sense that it's just a recipe. It's really a mechanical procedure that you can apply whenever you need to. Okay? And you'll get some practice on that with the exercise sets as well. And again, that said, you know, it's good to have a syntactic understanding or a syntactic facility with duals, but don't ever forget what's the point of the dual. The point of the dual is to upper bound, and as we'll see, upper bound tightly the optimal objective function value of the primal. Okay, so I promised connections to the Hungarian algorithm. So how do we interpret this dual? Well, these P sub v's are exactly the prices we were using in the Hungarian algorithm. Exactly. It's exactly the same thing. In fact, if you think about it, like, you might have wondered, you know, Kuhn, back in like the early 50s, why did he ever think to, like, all of a sudden, you know, you're trying to compute a matching, right? So everything about your input seems to be just about edges, right? You have a graph, you have costs on edges, you want a matching is a subset of edges. Why would you suddenly attach numbers to vertices in your algorithm to make decisions? Like, how would you ever think to do that? I gave you kind of a ahistorical story at the time by analogy to push-relabel max flow algorithms, but actually push-relabel max flows from the mid-80s, Kuhn's algorithms from the mid-50s. So that was kind of a little lie back then. So how would you ever come up with the vertex prices in the first place if you knew duality? Then it would be clear there's relevant dual variables. Dual variables correspond to primal constraints. Matching constraints are on the vertices, so you get dual variables on the vertices. Okay? So that's why Kuhn decided to have these prices. Linear programming duality was actually quite new at that point. It was only invented in the late 40s, really, but Kuhn was one of the early experts on it. So he certainly knew about LP-duality when he was inventing the Hungarian algorithm. Okay? So that's how you should think about these dual variables. They're just the prices from the Hungarian algorithm. And if we think a little bit about what feasibility means in the dual, and then especially if we think a little bit about complementary slackness, all of a sudden the Hungarian algorithm does not seem so mysterious. Okay, it seems like something that would just fall out of the general principles you're learning in this class. So note, what does it mean for a vector of prices to be feasible for the dual? Well, so it just means all those constraints are satisfied. Let me write them in a different way. Let me subtract the two p's from the right-hand side. Okay, so that's just by definition. That's what it means for p to be feasible. Now, this thing on the left, this is a quantity that you have seen before. Remember what we called that? Good. We call it the reduced cost in the Hungarian algorithm. And in the Hungarian algorithm, we had two invariants referring to reduced costs. The first invariant was exactly that the vertex prices should always have the property that all reduced costs are non-negative, which we now understand is just saying the vertex prices should be feasible for the dual. Okay. So first invariant of the Hungarian algorithm. Okay. Not only that, what does complementary slackness mean for this primal-dual pair? Okay. So complementary slackness always says that if some decision variable has a non-zero value, then the corresponding constraint should be tight, should hold with equality. Now here actually there's only one set of non-trivial complementary slackness conditions, not two like before. The reason is that we always have equations in the primal. Okay? So it's vacuously satisfied that no matter what you're doing in the dual, the corresponding primal constraints are tight, just because they're equations. So the interesting complementary slackness condition asserts that whenever a primal variable is non-zero, i.e. strictly positive, the corresponding dual constraint should be tight. What does it mean for a dual constraint to be tight? It means it holds with equality, which means that this holds with equality, which means that the reduced cost is zero, which is what we were calling tight edges. And now maybe it's sort of more clear why we were calling them tight edges. So complementary slackness then translates to whenever you have a non-zero primal variable, it should be the case that your reduced cost is zero. The second invariant, the first invariant of the Hungarian algorithm was all reduced costs of all edges are always non-negative. The second invariant was only about the edges in the matching, okay, which corresponds to a positive primal variable, and it said that the edges in the matching better be tight. Okay? That was the second invariant. Okay. So then with respect to our general paradigm, where you have these three conditions which together imply optimality, and you have the idea of maintaining two at all times and working toward the third, we now see that the Hungarian algorithm is exactly an instantiation of that paradigm, where the constraint, the condition that you drop initially is the first one. Okay, so remember the Hungarian algorithm starts with the empty matching, so that's not primal feasible, it's not a perfect matching. But the two invariants say that at all times, it maintains conditions 2 and 3. It maintains dual feasibility, it maintains complementary slackness. It terminates with primal feasibility, a perfect matching, and therefore by just complementary slackness conditions, it's got to be optimal. Okay? Yeah. And so in general, this kind of algorithm where you relax primal feasibility, maintain dual feasibility, and maintain complementary slackness, that's known as a primal-dual algorithm. Hungarian algorithm being possibly the most canonical example. Okay. All right. In our first example, with maximum flow, we were able to deduce some interesting properties about linear programs just because we already knew the max flow min cut theorem was true. Okay? Or if you like, we knew the 4% algorithm was correct. Same thing here. Just by knowing that the Hungarian algorithm terminates, successfully satisfies all three of these conditions, we can deduce some interesting facts about this primal dual pair. So first of all, just in general, if we look at the optimal objective function value to the dual linear program, just by weak duality, that's at most the optimal objective function value of the primal. Remember, this is the direction weak duality goes in when your primal is a minimization linear program. The min is always at least the max. Okay? And then on the other hand, the optimal solution to the primal linear program can only be less than the cost of a min cost perfect matching. Okay? Why? Well, what is this? That says look at every single matching, perfect matching that exists, and pick the cheapest one. What is this? This says iterate over every feasible solution to this linear program, which includes matchings as a special case, plus other fractional stuff, and pick the best one. Okay? So the linear program is minimizing over only more possible solutions than the perfect matchings, so the minimum is only going to be smaller. So that's why this inequality holds. Okay? On the other hand, we studied the Hungarian algorithm, and we concluded that that algorithm is guaranteed to terminate as long as the graph has a perfect matching. And when it terminates, as we now see, it terminates with primal and dual feasibility and complementary slackness all satisfied. Remember, when complementary slackness is satisfied, everything has equal objective function value. Okay? So put differently, the Hungarian algorithm terminates with a 0-1 feasible solution to the primal, and with a dual feasible solution with complementary slackness holding. That implies that the matching is optimal and that the dual is optimal. So equality always holds. Okay? So we wouldn't know this if we hadn't analyzed the Hungarian algorithm. Okay? We'd only know the inequalities. But the Hungarian algorithm proves, it exhibits, no matter what the graph is, a matching and a dual solution that's feasible that have exactly the same value. And that can only happen if both of these inequalities are equations. Just like with max flow, the fact that both of these inequalities are equations is interesting. Why is this always being an equation interesting? Okay, so that says there's never a gap between the optimal solution of the primal and the dual. And that's a special case of strong duality. Okay, so we verified strong duality in a second class of linear programs corresponding to matchings and their duals. That's the first interesting thing. We'll see strong duality holds completely generally, but it's nice seeing it in some special cases first. Why is it interesting that the second inequality is an equation? Well, this is just like when we were talking about cuts. The fact that there's never a gap between the linear programming optimum and the best perfect matching, that says you're always guaranteed to have an optimal solution to this linear program that is 0-1. Okay? Fractions do not help you come up with a better solution. Okay? So matchings are always optimal amongst feasible solutions to the linear program. Okay? So it's a second natural linear program guaranteed to have optimal integral solutions. Okay? So any questions about any of this? Okay. So the rest of the lecture I want to talk about strong duality. So any questions before strong duality, the statement and a bit about the proof? Okay. Okay? So this is a theorem. This is a major theorem. Okay? This is really interesting and not particularly trivial. Suppose you have a primal-dual pair of linear programs in any of the forms of linear programs that we've discussed. Okay, it doesn't matter which one. So whenever a primal-dual pair, P and D, are both feasible, then in fact, there's no gap. So weak duality always holds with equality. We already know this is true for max flow linear programs and their duals. We already know this is true for bipartite matching and their duals, but actually it's true any linear program. Okay? There is never a gap. So remembering that what the dual means is a particular method for bounding the optimal objective function value of a primal, this actually says that you never need bounds other than the ones given by the dual linear program. Okay? There always will be a proof in the form of a dual feasible solution that actually proves the correct, tightest possible bound on the optimal objective function value of the primal. Okay? So there's never a need, in effect, to use anything other than dual solutions to derive bounds on the primal. But they're always good enough. Okay. So the assumption is that both are feasible. Of course, if either one is infeasible, it wouldn't make sense to talk about the optimal solution. We talked about on Thursday already from weak duality, we realized that if the primal is unbounded, then the dual has to be infeasible. Because again, by construction, any feasible solution to the dual would give you a bound on the primal. So primal unbounded only if the dual is infeasible. Similarly, the dual is unbounded only if the primal is infeasible. It's also possible that both the primal and dual are infeasible, but who cares about that? That's sort of not very interesting. Okay? But if they're both feasible, they both have a finite optimum, and those two optimal objective function values are the same. And based on what we've discussed so far, we can also think of this as generalizing simultaneously the maximum flow minimum cut theorem, Hall's theorem, and so forth. Okay, it's sort of a very general min-max theorem. All right, so before I talk about the proof, let me just make it clear why this is interesting and how you would use it. So the first few weeks of the course, I kept asking you over and over again for different problems, how do we know when we're done? And I taught you that the formal way to answer that question is to specify optimality conditions for a problem. That is, necessary and sufficient conditions for a solution being optimal. So from strong duality, we get optimality conditions at the very general level of just arbitrary linear programs. So from weak duality, we had sufficient conditions for optimality, but strong duality tells us that those same conditions are also necessary for optimality. Namely, if x and y are feasible for the primal and dual, strong duality implies that x and y are both optimal if and only if they have equal objective function value. Okay? So what we knew from weak duality was this direction. Okay? If that were true, then certainly that were true. That followed from weak duality. Sufficient condition for optimality. But strong duality says, actually, I guarantee you that there is going to be some xy feasible that have equal objective function value. There's never a gap. So if there's never a gap, then the only way to be optimal is if there's no gap between the primal and the dual. Okay? If there's any gap, you know, you can't, one of them at least has to not be optimal. Similarly, when I introduced the complementary slackness conditions, I presented them as a sufficient condition for optimality. But now that if we assume strong duality, then in fact it's a necessary and sufficient condition. It's an optimality condition. Okay? And that's because complementary slackness holds if and only if this holds. And I ask you to think about that on the exercise set 4. Okay? Although it's very simple. Okay. So everyone clear on that? So these are optimality conditions, which in some sense generalize all the ones that we've talked about thus far. Okay? How do you know you've solved a linear program optimally? Just exhibit a dual solution with exactly the same objective function value. One way to do that is to exhibit a feasible dual such that the complementary slackness conditions hold. Okay? Actually, those are the same thing. Okay? So that's how you know you're done solving a linear program. You have a dual satisfying complementary slackness, i.e. with the same objective function value. Questions about that? All right. So again, sort of the ultimate answer of how do we know when we're done. All right, so this is important enough results that I want to talk about its proof a little bit. I don't want to take the time to prove it in its full gory detail. That would take me over a lecture to do. But I want to spend the rest of today talking a little bit about the proof, and there'll be some further aspects of it on problem set 3. And so why am I doing this? What's my goal for talking about the proof a little bit? The main thing I want to do is demystify for you a little bit strong linear programming duality. Okay? At the moment, you know, it just seems kind of, I hope I've motivated why you would want this to be true. So I hope you think it's a cool result, but you shouldn't have some, fundamental intuition about why it should hold, other than the fact that it holds in a couple of examples. So what I want to do is I want to make it, develop your intuition so that it just seems super plausible that strong duality actually is true, while stopping short of giving a full proof. So let me tell you about sort of the ingredients. So I'll introduce these in turn. So first I'll talk about separating hyperplanes. Okay, so the ability to separate convex sets from points outside the set. This is just a fact that we're going to take on faith, but it's going to be eminently plausible. Okay, so I think you'll find this very easy to believe. Then what I'm going to focus on is I'm going to show you how, assuming this separating hyperplane theorem, we can derive from it something known as Farkas Lemma, which is basically like the feasibility version of strong LP-duality. Okay, when I actually spell out Farkas Lemma and talk about it, it'll be very clear that it's sort of very similar to what's going on in strong LP-duality. Okay? And indeed, from Farkas Lemma, you can derive strong LP-duality without too much trouble. And this will be on problem set 3. Okay? So my goals are to explain what is this result that we're going to assume, convince you it seems like it's got to be true, and then show you how this implies a feasibility version of strong LP duality. Okay? So that's the plan for the rest of the lecture. All right. So, I need a new board for this. Separating hyperplanes. We actually sort of talked about separating hyperplanes a week ago. It was one of our applications of linear programming. If I give you a bunch of x's and a bunch of o's, and I want to know if there's a hyperplane which puts all the x's on one side and all the o's on the other. And we observe that that can be formulated as a linear program. So now, instead of separating x's and o's, we're going to be interested in separating a whole big set from some point not in the set. Okay? So that's the picture you should have in mind. All right, so here's the fact. So suppose you have a subset of Euclidean space. Okay? Think of this, if you like, as the feasible region of a linear program. And suppose that there are two things true about C. So first of all, assume it's convex. So what is convex? Convex means you're filled in. Okay? So that's an example of a convex region. A donut is a non-example. Okay? Formally, a set is convex if it contains all of its chords. Okay? So if you take any 2 points in the set, you draw a line segment between the 2 points, and you look at the midpoint of that segment, that should also be in the set. Okay? So obviously here, if I take any 2 points, the midpoint of the line segment between them was still in the set. Obviously in the donut, if I take these 2 points, the midpoint of the chord between them is outside the set, so it's not convex. Okay? So convex set contains all of its chords. Suppose also that this says closed. Okay, so closed in the topological sense, meaning the set includes its boundary. All right? So the unit ball would be an example, and the open unit ball would be a non-example. Okay? So those are the 2 hypotheses on this set. I want you to notice I'm not assuming that the set is bounded. Okay, that's important. So suppose you have such a set, and you have a point not in the set. Okay, so it's like this picture here. So think of that as C, and you have a point not in the set. Okay. Then there exists a separating hyperplane in the same sense that we were talking about a week ago. Okay. So you've got coefficients, 1 per coordinate. You've got an intercept. And it should be the case that all of the set C is on one side of the hyperplane. So we look at the dot product of alpha with x, that's at least beta for all x and C. And Z should be on the opposite side of the hyperplane. Okay? So that's the statement. Okay? You show me any closed convex set, not necessarily bounded, show me any points outside the set. I can slice space so that the set's on one side and the point's on the other side. Okay? So in 2 and 3 dimensions, I hope you find this intuitively like kind of obvious. Like it just seems like it's gotta be true, right? And then if you actually wrote down a formal proof of the fact, the formal proof you'd write down actually wouldn't depend on the number of dimensions. It would hold no matter how many dimensions you had, okay? For those of you that know sort of a little bit of mathematical analysis, like Math 115 or 171, and no worries if you don't, but if you do, how would you do it? It's not very hard if you have a little bit of training. You just say, well, let's look at the nearest neighbor to Z and C, okay? So maybe it's closest to this point here, okay? This is where you use the fact that C is closed. By virtue of being closed, there exists a nearest neighbor in C to Z. Then you draw the chord between Z and its nearest neighbor. And then you just look at the midpoint of the chord, and you look at the perpendicular hyperplane, perpendicular to the chord. Okay? And that works. All right? And again, the algebra you'd write down to verify this, even in 2 dimensions, just works in an arbitrary number of dimensions. So where do you use convexity of the set C? Well, you want to argue that all of C is on the opposite side from the point Z. Right? So if C wasn't convex, then it could sort of wrap back around the other side of the separating hyperplane, and it wouldn't be a separating hyperplane. Okay? But by virtue of being convex, and by virtue of this being the nearest neighbor to Z, and how we chose this, all of C lies on the left. Okay. So again, the point is not to understand that at a detailed level. It's more just to convince you that if you really, if we really wanted to have a formal proof of this, it wouldn't bother us. We could do it. Okay? It would just take us, 45 minutes or whatever. Right. So that's the separating hyperplane theorem. So for the rest of class, we're just going to accept that this is true. All right. So any questions? All right. So this we just assume. So I hope you find it eminently plausible. Now I'm going to prove this implication. So I need to tell you what Farkas's lemma is, how to interpret it, and how to derive it from the separating hyperplane theorem. All right. So what's the point of Farkas's lemma? So this actually predates linear programming duality. This is from somewhere around the turn of the 20th century. So what Farkas's lemma is trying to answer, it says, suppose you have a system of linear equations and linear inequalities. That is, suppose you have like a linear program, but you delete the objective function. Okay? So you just have equations and inequalities. And you're trying to understand, does it have a feasible solution or not? Now, if I wanted to convince you that this kind of system was feasible, wouldn't be hard. I'd just show you the feasible solution. You'd verify all of the constraints. What if I wanted to convince you that this linear system of equations and inequalities was not feasible, that there was no feasible solution? I can't very well enumerate every conceivable solution and show you by one that each is infeasible. So how would I convince you of infeasibility? So Farkas's lemma gives an answer to that question. So suppose you have a matrix A, as usual, m by n, and suppose you have a right-hand side B. Farkas's lemma asserts that exactly one of the following two conditions is true. So there exists a non-negative x. So this is in Rn. And the way I encourage you to interpret one is, imagine this was the system we really wanted to know if it was feasible or not. Okay? So we have this constraint matrix A, this right-hand side B. We want to know, is there a non-negative solution to this linear system of equations or not? Okay? And then the point of statement 2 so there exists a y. This is going to be now an Rm, such that y transpose A is component-wise non-negative, and y transpose B is strictly negative. Okay? So again, just to be clear, right, so B and y are both m vectors. This is an inner product. This is a scalar. So it's just a number we're talking about being less than 0. A is a matrix, right, m by n. So y transpose A, that's a linear combination of its rows. So that's going to be an n vector. So this is really saying component-wise. For each of the n components, it should be non-negative. Okay? And the way to think about this, I told you one, we're thinking about we want to know whether or not this is feasible or not. The way to think about two, and this will become really clear in a second, but think about two as being ways of proving infeasibility of the first linear system. Okay? So it's going to be the case that solutions to the second system will give infeasibility proofs for the first system. So just like with linear programs and linear programming duals, there's lots of different variants, bells and whistles, inequalities, equations, non-negative variables, general variables. Same thing with Farkas's lemma. Okay, so I've given you one version where in our first linear system we have equations, we have non-negativity, but all of the other ones have them as well. Okay, and given this one Farkas's lemma, you can derive the other ones basically black box, and you'll get some practice with that on problem set number 3. Okay, but this is the one that's easiest to prove from scratch. All right. So proof sketch. Well, we're asserting that exactly 1 or 2 is feasible. So there are two things we have to rule out. We have to rule out them both being feasible. That's going to be easy. We have to rule out that both are infeasible. That's where we're going to use the separating hyperplane. Okay? So why can't they both be feasible? So I claim there's no way that you both have a solution to 1 and you also have a solution to 2. Why not? Well, consider the number of y transpose AX, where X is the alleged solution to 1, Y is the alleged solution to 2. So X is supposed to be non-negative. Y transpose A is supposed to be component-wise non-negative. So this is certainly going to be a non-negative number. On the other hand, if we look at exactly the same number, by this constraint, this is equal to B. So this is Y transpose B, which is, by assumption, negative. Okay? So this is obviously a contradiction of the assumption that both of them are feasible. Okay? And again, there shouldn't be any mystery here. This is by design. Okay? How would you convince someone that a linear system of this form had no solution, was infeasible? Well, one convincing proof of infeasibility would be to figure out a way to multiply the rows of the matrix so that the resulting n vector you get is non-negative, and yet the dot product of y with the right-hand side is strictly negative. Okay? So you should interpret this as kind of an obvious proof that 1 is infeasible. Okay? Or conversely, if you want. Okay? All right, so this is the easy part, and this is really just by construction of linear systems. Okay, so we're not worried about them both being feasible. That's not going to happen. All right? What's highly unclear is why it can't be the case that both 1 and 2 are infeasible. Okay? So that's what we have to rule out. That's what's left to do. How are we going to do that? So we're going to show that if the first one is infeasible, then the second one is feasible. Okay? So that is, it's impossible for both to be infeasible. That will complete the proof. Okay? And one way to think about this is that, okay, so we asked the question, how would you prove to somebody the infeasibility of a system of linear equations and non-negativity constraints? You just exhibit the suitable row multiplier. But then you can ask the question, it's like, okay, well, is that good enough? Or are there going to be infeasible linear systems where you can't find such a proof of infeasibility? So what we're asserting right now, what this is really saying, is that whenever this is infeasible, you are guaranteed to have a proof in the form of a y which verifies its infeasibility. Okay? And I hope phrased this way, the parallel with strong LP-duality is very clear. Okay? So what are duals? They're upper bounds on the optimal objective function value of the primal. What's strong LP-duality? It says you don't need any better upper bounds. Okay? Dual solutions are always good enough. They always prove the best possible, tightest upper bound. Here, we're not really talking about optimizing, but it's a feasibility version of the same thing. Okay? So the primal, how do you know it's infeasible? You look at these particular types of proofs, again, with multipliers on the rows. And the guarantee is that there always exists, whenever it's infeasible, there always exists a proof of this form. Okay? So it's very much in the spirit of strong LP-duality, just a feasibility version of it. Okay. Oh boy, this is going to be tough. All right. Let's do this. Okay, so assume 1 is infeasible. What are we tasked with? We got to find a y. Right? So if 1's infeasible, we want to prove 2 is feasible, we got to find a y. Where are we going to get a y? We're going to get a y from the separating hyperplane. Okay. All right, so to apply the separating hyperplane theorem, we need a closed convex set, and we need a point not in the set. Okay? So here's a nice definition of a set that's going to work really well for us. So define Q. Let me write this down, and then I'll explain it. This is an Rm. So there's two different ways you should think about Q, okay, that are equivalent ways, but they're both useful. So first, we have this constraint matrix A, okay? Now, we have this right-hand side B that we care about, and it's infeasible, okay? But so, like, let's forget about B for a second, okay? So B by assumption is infeasible. Let's just say, you know, which right-hand side's D would give us a feasible linear system, okay? AX equal D and X non-negative. So in other words, what are the options? What could we replace B with to recover feasibility in 1? Okay? And that's if you just parse this directly, that's how you should understand this. Right? So it's all D so that there's a solution in X non-negative AX equal D. All right? That's the first way to think about Q. Here's the second way to think about Q. Okay, so which D's are feasible? Actually, if you think about it, it's easy to figure out which D's you're going to get, right? Namely, range over all non-negative x's. So now I'm going to hide D. Okay, forget about D for a second. Range over all non-negative x's, and look at all the induced AX's, all the induced right-hand sides. Okay? That's going to give me all of the D's of this form. Okay? So in other words, to each non-negative x, there is a corresponding right-hand side for which it is feasible, namely the right-hand side D equal to AX. Okay, so each choice of non-negative x's gives me a D. All right? Okay, so what is that? So what is AX with X non-negative? That's just a linear combination, a non-negative linear combination of the columns of A. Right? So ranging over all non-negative x's and looking at AX just says, look at all non-negative linear combinations of the columns of A. That's also called sometimes the cone generated by the columns of A. Okay? All right, so that's Q. So again, to apply the separating hyperplane theorem, we also need a point not in the set. So what's our point not in this set? B, exactly. So remember, this is all the right-hand sides, which we actually are feasible, and by assumption, we're not feasible for B. So B does not belong to Q. Okay? So that's good. Also note, so to apply the separating hyperplane theorem, Q has to be convex and closed. It's convex just because of equations and inequalities and taking the intersection. That's going to be a closed set. And also, if you think about it a little bit, you see that Q is convex. And either you can think about this because it's the intersection of convex sets, so sort of affine spaces and inequalities and half spaces. Or remember, what does it mean to be convex? It means if you take 2 points in the set and you take the midpoint, that's still in the set. What are Q? Q are non-negative linear combinations of the columns of A. If you take one non-negative linear combination and another non-negative linear combination, and you average them, you get another non-negative linear combination of A, of the columns of A. Okay? So there should be no mystery about Q being convex either. Okay? So the separating hyperplane theorem applies. Okay, so Q is our C, B is our Z, and then what do we get? We get an alpha and a beta so that these two things are true. Okay. So by separating hyperplane theorem, there exists alpha in Rm, beta in R, such that alpha transpose D is at least beta for all D and Q. So for all feasible right-hand sides, alpha transpose D is at least beta. But for our infeasible right-hand side, alpha transpose B is less than beta. Okay? So I haven't done anything fancy. I've literally just, over here, we were just verifying the hypotheses of the separating hyperplane theorem. We just applied a black box, and by the statement of that separating hyperplane theorem, we're assured of such an alpha and beta. Okay? All right, so just a quick simplification, and I'll ask you to justify this on exercise set 5. Without loss of generality, we can take beta equals 0. Okay? In general, in the separating hyperplane theorem, beta is just some real number. But if you think about it for a little bit, you realize, oh, because Q is a cone and closed under multiplication by positive scalars, actually, we're basically going to need to take beta equal to 0. Okay? But it's not obvious. I'm going to ask you to think about that outside of class. So we get the beta is equal to 0, and then we have some vector alpha so that this is true. Now, compared to what we're looking for, what are we trying to do? We're trying to exhibit a feasible solution to this linear system. We're trying to exhibit a y. What are the two properties y is supposed to have? Y transpose this infeasible right-hand side b is supposed to be negative. Well, that's kind of good, right? So if we identify alpha, okay, sort of the normal vector of the separating hyperplane, if we identify alpha with y, then this holds. Okay? So if we're so lucky that alpha also satisfies this, then we're done. Okay? So what is the feasible solution to the second system? It is the normal vector to the separating hyperplane between the infeasible right-hand side and all of the feasible right-hand sides. Okay? All right, so to check, so need to check, and then we're done. You need to check that alpha transpose A is non-negative. Okay? All right, so, but let's just remember what this is. All right, so A is m by n. Right, so we're now doing a linear combination of the rows of A. Okay? So this is going to be an n vector indexed by the decision variables. Okay? So just vector matrix multiplication. This is alpha transpose, dot product with the first column of A all the way up to alpha transpose nth column of A. Okay. So this is a m vector. Okay. No, sorry. N vector. Okay. So what are we trying to prove? We're trying to prove that every one of these coordinates is non-negative. Right? If we can do that, we're done. We can plug in alpha as y, and we're all set. So here's the claim. First column of A, totally in Q. Do you see why? Well, what was one of the ways to think about Q? Right, one of the ways is as the feasible right-hand sides. But we have a second way, non-negative linear combinations of the columns of A. Well, column 1, definitely a non-negative linear combination of the columns of A. Same thing for all of the columns. Okay? Every column is a special case of a non-negative linear combination of columns of A. What do we know about everything in Q? Well, the separating hyperplane tells us indeed all of the columns of A then have to be on the other side of the hyperplane. Okay? So this is non-negative by virtue of the first column being in Q and the separating hyperplane guarantee all the way up. All right? So that's Farkas' lemma. Any questions? See you Thursday.